Okay, as you said, today I'm going to be talking about the low fragmentation heap on Windows 7, specifically for 32-bit. Before we start, I always like to start with why are we doing this, right? A lot of things have changed since Windows XP. There's new data structures, things are more complex. In my opinion, memory management is even more complex. And with these complexities, you need to know more to get reliable exploitation. Stack overflows, while they do happen, are basically dead, right? Your simple 4-byte overwrites, when you were doing coalescing or unlinking, are basically dead. And there really hasn't been any documentation on how the low fragmentation heap works. So I decided to waste 9 months of my life and reverse engineer NTDLL and give the findings to everyone else. Okay, what we're going to talk about today first. Unfortunately, there's some boring stuff. We're going to talk about the data structures. There's a lot of new data structures. The way they work has changed a lot. Then we'll go into architecture. Free lists are still present, but they're not used how they were in the Windows XP Server 2003 days. They changed a lot since then. Then we'll finally go into core algorithms. We'll figure out, how allocations and how frees are made. I'm only going to briefly go over the back end due to time constraints. But if you want any more information, I have listed my paper that was posted at Black Hat on the same subject, and a different set of slides as well that actually includes more information. So if you are interested, you can go over that and probably get some more stuff from it. After we get up all the prerequisites, the algorithms and the data structures, we'll talk about tactics and heap determinism. That is, getting the heap in a state which you want it before you run your exploit. I personally think is probably the most important thing to learn now, as opposed to even exploitation techniques. That being said, I've left exploitation techniques for last. I'm going to talk about a technique I named Ben Hawks number 1, because Ben Hawks is a complete badass. And we'll see what he did. And then during my research, I found my own new technique for exploiting heap overflows on Windows 7. I like to get my terms set because so many people use so many different terms. So when I say block, 1 block equals 8 bytes. When I say chunk, that chunk can be measured in blocks or bytes, but it is a contiguous piece of data. There's a data structure called the heap list lookup. I will also refer to that as the blocks index. This blocks index will have 2. The first blocks index, which manages chunks below 1024 bytes, and the second blocks index, which manages chunks below 16K. Finally, I don't use the term heap bucket for memory that is actually acquired and used by the manager, because in the Microsoft debugging symbols, they actually use this for a 4-byte data structure solely for keeping track of size and indices. I'll use the term heap bin or user blocks for the actual data that's used in the heap. On we go. Core data structures. Heap, or the heap base, is the first data structure you have to talk about. It's the heart of every heap that's created within Windows. It's a very large data structure, but I've listed the new entries that were introduced to it in Windows Vista and Windows 7. There's a thing called the encode flag mask. This is set when the heap is created. It is set to a specific value, and it's tested against addresses. And if it returns logically true, that means the chunk was encoded, which we'll talk about later. If it returns false, it assumes the chunk is not encoded. The encoding is a randomly, I guess I should say pseudo-randomly generated value, again, when the heap is created, and it's used in that encoding sequence when encoding heap chunks. You have the blocks index, which we'll talk about next, and then a pointer to the free lists. And this isn't 128 free lists like you had before. This is kind of a pointer to this first chunk in this overall list of free chunks in the heap. And I have a diagram, and hopefully that'll clear things up later. And obviously it's going to have a pointer to the front-end heap, which is the low fragmentation heap. There is no more look-aside list in Windows 7 as there was in Windows XP. Now we have the blocks index, or the heap list lookup structure. This structure is used for tracking free chunks, and it's also a linked list structure. There's multiple ones. As I said before, they kind of are used to measure different sizes, and that array size will tell you in blocks, not bytes, the sizes of chunks that it's going to maintain. That being said, you also have things called list hints, and these list hints are very much like how free lists work, right? You have a list hint for a certain size, and it will point into this overall free list structure. And just like Windows XP, there's the listed use long bitmap. This is an optimization to determine what list hints actually have chunks associated with them. But now, since there is multiple heap list lookup structures or blocks index structures, you can't have a single bitmap in the heap. You're going to have a bitmap basically for every single one of these list lookup structures. Obviously, there is the low fragmentation heap data structure, and you can probably guess this manages data for the low fragmentation heap. Although there is only an array of 128 heap bucket structures, there is an algorithm to figure out what sizes, as the low fragmentation heap can manage chunks below 16K bytes. So there's an algorithm used to figure out what bucket is populated. And this brings us to the heap local data. The sole purpose of this heap local data structure is to hold heap local segment info structures. Again, there's 128. There's an algorithm used to figure out which local segment info structure can be used when requesting certain sizes. The local segment info structure, it holds pointers to two other key data structures. There's a hint and an active subsegment. And these heap subsegments here are actually used to track data. So there's a very parental aspect of all these data structures. And I don't know if you can see it, but they kind of each have a pointer back to its parent. So each individual data structure knows what parent it came from. And I made an awful diagram in Visio that'll be in the next slide, and it should kind of show you how they're all related. These heap subsegments, they contain two things: a pointer to the user blocks. This user blocks is preceded by this user data header. This user blocks, this is actual committed memory that will be used by the low fragmentation heap. This isn't just another data structure to keep track of sizes. This is committed data that we used when freeing and allocating memory. The way it keeps track of these user blocks now is done with this interlock sequence structure, or the aggregate exchange. It does two things. It keeps track of depth, and depth just says how many chunks of a certain size does my user blocks have, right? It's just a counter, basically. The next one is the free entry offset. The free entry offset tells you, within this overall big chunk of memory, where's the next free chunk that's available for the allocator to grab? Or, when you're freeing, where do I, what index do I update? Each chunk in the heap, lastly, will contain this chunk header. And if you know anything about the heap, every chunk has an 8-byte chunk header. The thing that changed in Vista and Windows 7 is they started encoding the size and the flags and the checksum. Things like the bitmap flipping attack, which I'll talk about in a bit, was kind of nulled out by this encoding because you couldn't predictably overwrite sizes anymore. That being said, they only encode the first 4 bytes of this 8-byte data structure, so there still are things you can do. This is kind of an overview of how all these things are related, right? You have this heap, and this heap contains multiple heap list lookups, and the low fragmentation heap has a heap local data, which has segments, which have subsegments, and those subsegments are used for actual allocation. Hopefully this kind of gives you an aspect of, like I said, this is a very parental structure for deciding how to allocate free memory. On to the architecture section. back in the day, you had 128 free lists, right? And you also had a special free list 0, which kept track of chunks that were greater than 1,024 bytes. It was pretty easy. The lists were terminated with pointers to themselves. So it was a doubly linked list, and if the list was empty, it pointed back to itself. This was, again, it could be used to leverage code execution, because if you could overwrite these pointers, tricking a list into thinking it was populated when it was not, you could overwrite address, which was on the heap base, which contained a lot of pointers, specifically a function pointer, the commit routine, and if you overwrote that, tried to commit more memory, you had code execution. That's kind of changed. The dedicated free list have gone away. Now you have the list hints for certain sizes, but instead of terminating when they're out of that certain size, it points to the next biggest chunk in the overall free list. And that, with that being said, it now works differently. There's not termination for a specific list. It just goes to the next biggest. And finally, the last biggest chunk in the free list now points back to the free list pointer in the heap base. With that being said, the forward link and back link in these blocks index list hint also are used as a dual purpose, right? The backlink on the blocks index list hint sentinel nodes will actually be used for two things. One, it is a counter. And when this counter is exceeded, the low fragmentation heap will actually start being used for that specific size. If a low fragmentation heap is enabled for that specific size, it will actually contain a pointer to a heap bucket structure. You have to actually enable the low fragmentation heap for specific sizes. Now, while it may be enabled by default as you read in documentation, you have to make multiple allocations to actually get it enabled. It kind of looks like this. This is a very simple heap with only 5 chunks in its free list, right? And as you see, you have your heap data structure, right? And then you have blocks index, and that blocks index has 3 chunks for free list hex 6. That's 30 hex bytes, right? And the first 3 chunks are pointed to there. But instead, when the last chunk for 6 blocks is done, it doesn't point back here. It actually points to the next largest chunk, which is a chunk for 38 hex bytes. And again, that only contains 1 chunk. When it's terminated, it's not pointing back. It goes to the next largest chunk. The larger chunk is at the bottom. It is the last chunk in the list, which it does point right back here to the free list again. And as you can see, I'm sorry it's kind of small, but the backlink in some of these, you'll see I have counter listed. That counts how many times it is allocated for that size. Now, if you look at free list for hex 40 bytes, you'll see that the forward link is null, and the backlink actually contains an address. That's an address to a heap bucket structure, and that just denotes, for that size, use a low fragmentation heap. I like to think of this as a circular organization of chunk headers or a cock. And these cocks are much like highway systems, right? Where you don't want to start at the very beginning. You want that list hint to point you to the nearest tributary by you. There may be a situation where you need to start at the beginning and look, but you would much rather get on the nearest tributary to where you're going instead of starting at the beginning. So hopefully the diagram and my devised acronym will help people understand how these new free lists work as opposed to the old ones. On to allocation. Allocation obviously is going to be covered first because you can't free memory unless you allocate it. Allocation, first thing it's going to do is it's going to round whatever size you pass it to the nearest 8-byte value. Even if you pass null, 0, to the user land memory manager for the Windows heap, you will get 8 bytes back. So once it figures out this nice round number, it's going to start traversing those blocks index structures. And like I said, they're linked lists, so it will say, hey, can this cover the size I'm trying to allocate? If it can't, it'll try the next one. If the next one is null, as in the linked list is empty, it'll say, use this special value, and it says block size equals blocks index array size minus 1. That's very similar to how freelist 0 worked on Windows XP. It keeps track of all chunks greater than a certain size, greater than the array size that this block's index can hold. Now that it's found a blocks index, it's going to get that free list or list hint. And by the way, I will use the term free list and list hint interchangeably throughout, this presentation and also the corresponding paper I have. You have this free list. If that free list backlink contains a heap bucket, that means we can use a low fragmentation heap. If a low fragmentation heap fails to allocate memory for some reason, right, you're going to use the back-end allocator. When all else fails, the back-end allocator will be used to gather memory. Just keep that in mind, because there's certain nice situations in which you can cause the front-end manager, the low fragmentation heap, to fail, and you know that the back-end manager will be used. And unfortunately, I didn't have time to fully cover the back-end manager. Again, you can read the paper or check out the previous slide deck I had, but we'll just say that it does a few things. First, it takes that free list and checks the backlink, and it'll increment the counter. So every time you allocate for a certain size, it's going to try to increment this counter. Once this counter threshold limit is exceeded, it'll say, okay, now start using the low fragmentation heap for this size. Basically, they don't want to turn the low fragmentation heap on for a size that's only going to get allocated once in a blue moon. They want to make sure that there's going to be frequent allocation. That's how it was designed to be used. Finally, it's going to, after it's done updating those heuristics, it's going to look through those blocks index, try to find a chunk. If it can't find one of the exact size, it'll look for a bigger one. If it finds a bigger one, it will split it up, give what you wanted back to you, put the other back in the free list on the heap. If it can't find a sufficiently sized chunk, it will try to extend the heap. That is, it will try to commit more memory that can be used by these free lists. If that fails, you're shit out of luck and you're not getting memory, and your program is probably going to crash. Now we can move on to the good stuff, the low fragmentation heap, or the front-end manager. Like I said before, you have a heap bucket address that is used to denote low fragmentation heap usage. With that, there's actually an equation to get the address of the low fragmentation heap based on the address of this heap bucket. It's not passed. So Ben Hawks actually in his 2008 RuxCon Black Hat material suggested that if you could mess with this value, you could actually get it pointed to some fictitious low fragmentation heap, and from there do some overriding. But we'll ignore that for the time being and just say this is going to be your typical allocation. You pass it a size, which is denoted by a heap bucket. They keep track of what sizes they're responsible for. From there, you see you can get the heap local data. Then you get the local segment info. From there, it will get a subsegment. And that subsegment will be checked. The first thing it's going to do is it's going to get that aggregate exchange, right? And it's going to check the depth. Do I have any chunks left for this size that you're asking? It'll also check, do I actually have any memory? Have I ever had any memory for this size? If that's the case, it will actually get the chunk, and the way it figures out where the next free chunk is going to be, as is the first 2 bytes after that 8-byte header actually stores an integer value. And that integer value says, here's the offset to the next free chunk. And as you know, a lot of you are probably thinking, hey, that's user-writable data. And that's the premise of kind of my attack, that you have this unencoded 2-byte value that can be used and probably abused in the near future. But if all goes well, you get this chunk, it decrements the depth, right, because you've taken a chunk away, and it updates that free entry offset to the 2-byte value, which should point to the next available chunk in this block. If that doesn't work, you're going to need to allocate more memory for the low fragmentation heap, and it does this by the back end. The size that it requests is not arbitrary. It's actually a kind of complicated formula based on size. So it's saying, you know, if I want 30 bytes, do this mathematical formula, round it to the nearest page and line size. So, you know, the 4096 byte page on 32-bit systems, round it to that size, and then allocate it from the back end. This is the memory that will be used for that user blocks structure that I was talking about. But just because you have the memory doesn't actually mean you can start using it. It needs to be coupled with a heap subsegment. That subsegment is either acquired from a previously deleted one, or it's taken from a pool of data. And if you read the paper, again, since we didn't have enough time, you'll see an observations section. And there's a very neat thing that you can do if you can corrupt this pool of data that's used for heap subsegments. But now you have a subsegment and you have a bunch of data that you allocated. You need to couple it together, and you need to break the big chunk of data into little smaller chunks. And this is done in the initialization. Again, it looks complicated, but all it really does is figure out how big of a chunk of memory you allocated. And then it figures what size did you request. And every size that you requested, so we'll say, for example, 30 bytes. If you request 30 bytes and it just creates this, every 30 bytes it will write a new 8-byte chunk header. So the memory isn't actually split up. All this memory is contiguous and adjacent to each other. It just breaks them up by writing chunk headers, every so often. Two neat things. For the interlock sequence, the original offset is set to 2, because that offset is measured in blocks. That means, 16 bytes is the size of that user data header. That's before the actual data to be used. That's why the offset's set to that. The other neat thing to know is the last chunk in this in the user blocks, its 2-byte offset is set to -1. So if you see a chunk that has the first 2 bytes is FFFF, that means it's the last chunk in the list. Okay, here's the example I came up with. We'll say this is a fresh user blocks for size 30 hex bytes. You see that you have an offset of 2 for the first chunk, and then you have a depth. And I like to think of this as a big Sicilian pizza that's cut into squares. So say Nico comes over to your house and takes a piece of pizza, right? He takes one off. You see that the depth has been decremented by 1, and then the free entry offset has been updated to what was previously in there, and it was 8. Again, that being said, Nico wants another slice of pizza. He will take another slice, this time at offset 8. Its next offset is the value E, and he takes that. The depth, again, decremented, the free entry offset is updated. This is a pretty simple example, obviously, with a fresh user blocks, but it kind of shows you how each chunk is used, and it doesn't actually go away, obviously, but offsets and values are just updated. So try to remember the state that we're in here, because when I'm doing the freeing algorithms, we'll continue there. Now, when you want to free chunks, you've allocated this memory, whether the front end or the back end did it, you want to free it. It will check if it's null. If you pass it null, it will return 0 to you. If it's not 8-byte aligned, it will also log an error and return. So you can't pass non-8-byte aligned memory addresses to be freed. It will just, return error. Here's the neat part. So it checks that chunk header. So that 8 bytes that's before every heap chunk, it's going to check a value, and it's going to check the unused bytes value, which is at offset 7. Again, if it can be bitwise ANDed with hex 80, that means it was acquired from the low fragmentation heap. Otherwise, it uses the backend manager. The neat thing about this is unencoded data. So you could overwrite a chunk header that was allocated from a low fragmentation heap, change that unused bytes section, and the backend manager would actually attempt to free this chunk. I have yet to go farther into that, but obviously it wouldn't probably end up good and might lead to a situation that could lead to an exploitative scenario. Again, just a slight overview. It's going to get that chunk, right? And if the backlink doesn't contain a heap bucket, it's going to decrement this value by 1, that counter. Again, that means to actually enable the low fragmentation heap for a certain size, you can't do alloc free, alloc free. You need consecutive allocations so this counter will actually exceed the threshold. After that, it will coalesce the chunks above it and below it. Obviously, this prevents fragmentation, as does the low fragmentation heap, which was specifically designed to do. From there, it will safely link in this new chunk. And I'll talk about safe linking because it's kind of a direct response to Brett Moore's exploiting FreeList 0 on Windows XP Service Pack 2. Front-end freeing. It does a lot of the same things that the front-end allocator does. It's going to check this chunk header. And if the unused bytes are set to this certain size, well then it actually subtracts a value to get a new location of the chunk header. And this is kind of the premise to Ben Hock's exploitation technique that he came up with, and we'll talk about that in a bit. From there, it sets some flags, it gets the proper subsegment. Again, just like how the low fragmentation heap was acquired through allocation, the subsegment is not passed as an argument. It's actually calculated by doing some mathematical operations. By getting the current offset, which is in the aggregate exchange, and storing it in the first 2 bytes of the chunk that you just freed. I've left out a lot of data because there's all these corner cases which happen, but just generally think of when you're freeing a chunk in the low fragmentation heap, an offset is updated, and a counter is either incremented if you're freeing a chunk or decremented if you're allocating a chunk. We'll go back to this example of Nico eating your pizza. He's just taken another chunk, so we see the depth has been decremented, and the free entry offset is 14, and the chunk in the far right corner. Well, now if he frees this other chunk back, the first one he's grabbed, you see that the free entry offset is now 2 because he freed that first chunk at that offset. The depth is incremented by 1. The neat thing about this, right, is the biggest problem that a lot of people had when writing exploits for XP and XP2 was coalescing of data. If you freed a chunk and there was another free chunk by it, they would be combined. And you sometimes couldn't rely on what the size would be after they were combined. With the low fragmentation heap, since all these chunks are the same size, you know when you put it back almost where it's going to be, and you certainly know what size it's going to be. Before the next offset in this one was 8. Now it's 14 hex. Nico frees, puts another piece of pizza back in the box. The next offset is 2 because that was the next one, the one previously freed. The depth is again incremented. This works very much like a stack, right? It's the last in, first out nature. You free a chunk, it puts on. You take one off, it takes the first one that it put back. And that's nice to know when you're kind of doing some exploitation attacks where you want to get the same piece of memory back multiple times. But before we talk about that, we'll go into the new security mechanisms. The first one I like to talk about is heap randomization. Everyone's kind of familiar with this, right? It adds a certain random pad value to the heap, so the heap address isn't the same on every run of this certain program. This works, relatively well, but there's a few things to think about. There's only 5 bits of entropy. That's because there's 64K a line. So that means brute forcing, guessing the address of a heap is improbable, but it's certainly not impossible. And if you have multiple attempts at guessing these addresses, it gets downright guessable. The only neat thing that I realized when I was doing this was if you could influence heap create, one of the parameters of heap create, which is the maximum size of the heap, if that value plus that random pad integer wraps, that it ends up being greater than a 32-bit integer, it sets the random pad to 0. And when the random pad's set to 0, there's actually no more randomization. Unfortunately, it's hard to influence parameters to heap create. At least I haven't seen any real-world applications where you can, just-in-time compilers and things like that might be able to do it, but I just haven't seen any. The second thing is passing a very large value to NT allocate virtual memory usually will return in an error. And this error is going to, make this call fail, and the call to basically heap create will fail. I'm not saying it's impossible, but it's definitely wouldn't be easy to do. We talked about chunk header encoding. Those first 4 bytes are encoded, so you can't easily guess the size of a chunk or its flags or figure out its checksum without having an address link. You need to know an address to figure out how it was encoded, be it that it's based off address. Now that kind of sucks, and that basically killed bitmap flipping and some other techniques as well. But there were things that I did notice. That encode flag mask value, it's set when you call heap create. It's set to a specific value. But you see in these checks here that if encode flag mask is null, it just assumed chunks are not encoded. Well, if you could somehow figure out how to null out this value, you could therefore go about creating and manipulating heap chunks without having to worry about encoding. The sorry thing again about that is if you can make that happen, most likely the heap's going to be in a very unstable state because there will be chunks that were encoded at one point and now the sizes won't match up. Most likely you're going to get an exception somewhere. The other thing to note is obviously, you can also overwrite those first 4 bytes, right? The ones that are encoded, because there's a check in the decoding. Does the header and the edit bitwise ends it with encode flag mask? If that fails, it assumes the chunk is unencoded. The nice thing about this is you only need to really do it with chunks that are already on the free list, because otherwise in allocation and deallocation it would fail. The other is you semi-control this value. Now it can't be exactly what you want because it has to fail this logical check, but you do control the size, the checksum, and the flags. And this may be a good way to set up a barrier, so you don't get allocations past a certain chunk, amongst a few other things. And obviously, lastly, the thing I talked about, attack those last 4 bytes that aren't encoded. We can trick a chunk into thinking it was allocated from the back end when it was actually from the front end, and vice versa. So those are things that you can go about attacking even with all these security mechanisms. Bitmap flipping is dead, unfortunately. Where's Nico? I'm sorry. I'm sorry that bitmap flipping is dead because, you had good stuff last year and a bunch of people did some good techniques. We used this for our exploit that we used in Black Hat 2009. It was pretty chill. Unfortunately, before it was an XOR operation. Basically, they assumed you just do the opposite and flip the bit. They don't do that now. In allocation, it uses a bitwise AMP. The reason it does this is if you're making an allocation from somewhere, there's no way that can become, that the list can become populated when you're taking away from it. And they use bitwise OR for freeing. You can't take a chunk out of a list and it become populated. So while this does suck and it kills that exploitation technique, it's not as important because this information isn't on the heap base anymore. It's in this block index structures, and they just don't really hold as much integral, information as the heap base did. Safe linking is the last security mechanism I want to talk about. Before, what you could do with Brett Moore's attack, if you could overwrite the backlink of a chunk on a free list and get something inserted before it, that address would then point to the chunk that you just freed. The thing they do here is they make sure, does the insertions point backlink point to its forward link? And if it does not, it assumes that chunk's corrupted and it reports an error. But if it reports this error and doesn't terminate the process, you'll still see that the list hint is updated with this chunk. And the reason this is bad is in the linking process, it overwrites the forward link and backlink for the chunk that you just freed. If it isn't actually linked in, you fully control the forward link and back link. So you control 2 D words in this chunk if you can get this to fail, and it will be inserted into the free list. While getting that out, you'll have to deal with safe unlinking that was introduced in XP2 is still going to be a problem. You can get a false entry in the free list, and obviously, if you're doing heap exploitation, you know that's at least a very good starting point to where you want to go. Now on to the tactics. This is the part I think I like the most. The first thing I asked myself, even when I started doing this, was how do I enable the low fragmentation heap? The easiest way to do it is make 18 consecutive allocations for the same size. I can guarantee you after you do that, every subsequent allocation after that will be made from the low fragmentation heap. It's pretty easy. You just increment that counter until it turns on the low fragmentation heap for that size. The problem with this is, if you attach a debugger and like a Muni debugger, I wrote a plugin for it called Horse, and it'll show you what sizes are being used by the low fragmentation heap. Attach it to IE. The low fragmentation heap is basically enabled for almost every size, so turning it on isn't a problem, but having it in a state that you know about kind of is. And this leads us to the fragmentation portion of this. All of the exploitation techniques I talk about have a prerequisite of having chunks adjacent to each other, right next to each other, and in a state that you want them, whether free or allocated. You see at the top, here you have free, busy, free, busy, free. That's not really what you want for this technique. And I was talking to Alex Sudorov about, the techniques he was using, and basically we both came to the same conclusion. Make a large amount of allocations for the same size. The reason this works is because if you exhaust all the chunks for certain blocks, for certain user blocks, it will just create a new one. And that new one will be fresh. So if you know how the allocator works for a certain application, and you can make allocations for a certain size, you can massage the heap into a state that's going to be advantageous for you when attempting your exploitation. Well, now that you have blocks adjacent to each other, what exactly do you do with them? Obviously, since this is contiguous data, unlike the free list that could not be directly next to each other, a size, two items of the same size could be in 2 different pages of memory, really. I mean, technically that's, it could work that way. With a low fragmentation heap, everything is right next to each other. So if you get an overflow, you can overflow right into the next portion of data. C++ objects, there's going to be a V table there. One technique I really liked was, I'm going to butcher his name again, Peter Vuchtenhild, the technique he used in the Pwn to Own competition, where he wrote into an adjacent chunk but overwrote its null terminator. So now the string was much larger than the program anticipated because he overwrote the null terminator. And I kind of have an example of how that would work. The other nice thing to know about adjacent chunks is if you allocate free and then allocate without anything else doing that sequence for that size, you'll get the same piece of memory back. So if I make an allocation and then I free it and then I allocate it again, that same memory address is going to be given back to me on both allocations. The low fragmentation heap doesn't coalesce data. All it does is update depth and offset. Well, so you have adjacent data. Say you can't even overflow into a chunk. What other good is this going to do you? I think use after frees are probably the best example ever. The data isn't zeroed out every time a chunk is used in the low fragmentation heap. So what can you do? Make a ton of allocations, write data that you want there. Free all those chunks, the data is still there. From there, if you can, have a use after free situation, your data is still going to be there. In this example, I make 4 allocations, I write data to it. I free all 4 allocations, and then I make 4 more allocations. If you see, only 2 bytes have changed in each one. The reason is, those are the 2 bytes that are used for the next entry offset. Other than that, all your data is still intact. Okay, on to the real fun stuff, the exploitation. Remember when we were freeing and I talked about the way Ben Hawks decided that, hey, if you can change this certain value, it's going to update the chunk header to a different location. It's actually going to subtract, get the byte offset by 8 times that other value in the header that you also can overwrite that is unencrypted, or unencoded, sorry. Well, what good does that actually do you? The best thing you can do is free a piece of memory that's already in use. Be it with the first in, last in, first out way of a low fragmentation heap like a stack. If you free that memory and then acquire it, you know where it's going to be. So I think the best example I came up with was allocating 3 objects. Maybe that first object is a C++ object. Well, if you can subsequently overwrite into one of the other chunks that you've allocated from there and change that value to point to that C++ object and free it, that C++ object is still in use. But you can overwrite the data. And what's the first 4 bytes of most C++ objects that you know, do virtual functions? A vtable. Overwrite that vtable, call a function. There you go, you have code execution. Again, in my paper, there's actually a contrived example that you can compile and run, and it'll kind of show you how this would actually work. Now on to the exploitation mechanism that I came up with. But before we talk about it, I want to explain how the exception handling is done in the low fragmentation heap, especially in the allocator. What it does is it basically wraps everything in a try-catch block, all of it. What good does this do you? Remember when I talked about guessing addresses, and if you could guess them without any consequence of crashing the application, you could probably guess the address of heap base for one of the heaps in use in an application? This is your perfect candidate. With my technique and guessing, if you hit an address that isn't mapped in memory or is invalid, you'll get an exception. But that exception is handled and 0 is returned. And when a 0 is returned from this function, the memory manager says, oh, the low fragmentation heap failed, I'll just use the backend. So the worst case scenario is you still get your memory, but you get more tries at guessing more addresses. So I think that was neat, and John McDonald and I also kind of pointed that out in our last year's talk about XP exploitation. The look-aside list did the same thing. It wrapped everything in a try-catch-all. Okay, so we know the first 2 bytes of every chunk in the low fragmentation heap has the offset to the next free chunk. So what do? You're going to need to have chunks adjacent to each other, and you're going to have need at least a 9-byte, if not a 10-byte overflow. So we see here you have a fresh user block. The next offset on the first chunk is 8. From there, the next offset is E, from there, and so on. Well, what if you make an allocation and say we overwrite the next offset to be 1501 instead of E that it should have been? Well, now the aggregate exchange still hasn't been updated. You make another allocation for the same size. Now the free entry offset, which should point to E at this point, actually has the offset of 1501. This is bad. For this one, it would probably write off the page of memory, and you would get an access violation for accessing uncommitted memory. What can you do from here? What I came up with was, how about you pick a different size, not one that you've overflowed, and create a bunch of objects there, whether through the DOM, whether through some service, you know, depending on how the application works. So then you're going to have potentially, and most likely, another heap subsegment located in an adjacent page of memory. The nice thing with this technique, though, is it doesn't require the adjacent page. Now if we make an allocation for size 30 again, while we should be getting this chunk here, it's actually going to point to somewhere down here in adjacent page of memory. And from there, you know, you make that allocation, and then you have a right-end situation. The real neat thing, I think, about this is the page doesn't have to be adjacent to where you're at. If you can control those 2 bytes, you have 2 bytes multiplied by 8 of range that you can choose from. that means you can actually skip over portions of uncommitted memory into new sections, whether it be another heap that was created, whether it be some writable section of an executable that's in memory. You have FFFF times 8 of range to choose from. And from there, all you have to do is make an allocation and write out. And I think eventually I will get a vulnerability and I will write an exploit to show that this will work in the real world, and also that jumping pages or jumping through memory is going to be even more important, because with all these security checks, you don't want to munge as much data as possible. You want to leave everything as pristine as you can. And that's about it. Unfortunately, I had to go really fast, and I apologize for talking so quickly and kind of skipping over the details. But I think we can all say the data structures have changed, right? The free lists have changed. There are a lot of security mechanisms that were in place, but now even with all these security mechanisms, exploitation is not impossible. It just got harder. And just because it's harder doesn't mean it's impossible. And I think there's a lot of developers that assume that there's these security mechanisms in ASLR that they don't have to write secure code. It's obviously not the case. We're always going to figure out ways to, make exploits work. What other work can we do? First of all, here's the links to my paper, which is a wonderful 86 pages of boring reading material, if you're really into it. And then I have my other set of slides that are kind of more in-depth and detailed. But I want to see people writing Windows 7's heap exploits, reliable heap exploits. I want to see people, pick on the unencoded information. Unfortunately, with time constraints for all this stuff and getting it ready for Black Hat and Ekoparty, I didn't have time to investigate everything. There's still a lot of material that people can look into to figure out ways to take advantage of the heap manager. Be it that there's always, if they keep putting metadata along with user data, there's going to be ways to abuse it, and it's just going to take time and documentation to get reliable exploitation. So that's it. If anyone has any questions, you can ask, or we can grab a beer and we can talk or whatever. So thank you very much for being here.